So Sven asked me to speak about recent updates because he was aware that a large majority of the audience have been familiar with what we do for quite some time. So that's what I'm going to do. But I know that there's going to be some of you here who haven't the faintest idea who I am, so I thought I would start there. So I started my life not as a biologist, but as a computer scientist working in artificial intelligence. And when I switched fields in my late 20s, one of the things that I started to think after a few years was that perhaps the field was being blinded by the complexity of the phenomenon of aging and not seeing the wood for the trees. And I started to think, well, okay, what insights can we gain if we just take a really 40,000-foot view and start, well, so what is aging anyway? And I was a bit shocked by the fact that there seemed to be some disagreement about that. So I chose to view aging in this, I think, rather uncontroversial way as the combination of two processes, simply a lifelong process whereby the body generates various types of molecular and cellular alteration to its composition and structure, which I like to think of as accurately described as damage, simply because eventually those changes accumulate to a point that impedes the body and impairs its ability to do stuff, which of course is the late life process on the right. And obviously there are two approaches that have traditionally been adopted. First of all, when anyone really started living long enough that we became aware that there is this right-hand process, we started to try to eliminate these things rather in the same way that we try to eliminate infections. And obviously it hasn't worked very well. People are still getting these pathologies of late life, not all that much later in life than they used to. And of course, it's been more than 100 years now since some people have begun to realize this. We have had the field of gerontology largely because people decided, well, maybe instead we might get inspiration from the living world, from the fact that there is so much variation in nature, in the rate of aging, and even within species. Unfortunately, the attempt to make our metabolism run more cleanly and thereby to delay the point at which damage reaches the pathogenic level has also been totally unsuccessful so far. And at the end of the day, most people feel, and I think there's a large amount of truth in it, that this ultimately comes down to complexity, that if you tried the geriatrics approach, you get this kind of problem, the fact that so many things go wrong with us late in life, and they even exacerbate each other. And correspondingly, if you try to mess with metabolism and try to make it not do the thing we don't want it to do, you face a similar problem of complexity. And of course, these are understatements because they only refer to what we know about how these processes work rather than simply what we don't know, which is even more. And it occurred to me that really a common sense approach was, rather than to try to attack either of these component processes, to instead separate them from each other by being really comprehensive about repairing the damage before it gets to this threshold. And this seemed like quite a good idea, and I started putting it forward. And I was able to describe it in this 7-point manner, starting quite a long time ago now. And I seem to be still kind of getting away with this. And of course, rather more than getting away with it, those of you who are old enough to remember the somewhat mixed reception that this idea received back then will perhaps have been as amused as I was when, more than a decade later, the exact same idea was greeted with open arms by absolutely everybody. But those of you who are not still quite so old will probably think that this is quite surprising, but actually, of course, it happens all the time. So I thought that I would spend the bulk of my time just discussing what we've been doing recently, with the benefit and the generosity of a few people who were willing to bet on me. I was able to put together an organization a long time ago now, more than a decade ago, that has funded quite a lot of research over the years. And even though we have been quite small, our total annual budget has never risen above about $5 million. Nevertheless, the work that we've done has been quite effective. I thought I'd start actually by talking about our education program, which many of you may not even know about. But for the past 6 or 7 years, we have had quite a burgeoning one. It is mainly focused on on some summer internships. We take about between 15 and 20 interns from undergraduate level into both our labs and the various labs that we support. And it has really, it's made a bit of a name for itself. The professors that we have been giving these interns to have always said that they're the best interns they ever have, and we seem to have gained quite a reputation among the undergraduates themselves, to the extent that this program is now 50-fold oversubscribed each year. We only take 2% of the people who apply. But what I'm showing you here is a new expansion of that, courtesy of one of our funders, where we're taking on somewhat more senior people. This particular program that I'm showing you is already, as you can see from the date, it's already gone, but we will, of course, be doing it again. We take on people after at postgraduate level now, occasionally. But in addition to all that, of course, we fund not only work in our own laboratory in Mountain View, California, but also work in various universities and institutes around the world. And some of it has been rather conspicuously successful over the past several years. So I thought I would talk a little bit about the projects that are mentioned here, or some of them anyway, just in order to give some of you some updates. The top one, which was our first publication in Science magazine, was a bit of a breakthrough made by a group that we funded at Yale University. One of the, if you want me to really complain about the hallmarks of aging paper and all the things it left out, well, I'll start with the fact that the word glycation simply does not appear in the entire paper. And we decided that we ought to actually try and fix the problem of accumulation of glycation-induced cross-linking and thereby loss of elasticity, especially in the arteries. And this was a problem, of course, that's been around for a very long time, but the major component of it, namely this particular structure called glucosapane, had not been a significant area of research for a very long time, simply because people had basically given up on the idea that they might actually be able to do anything about it. And we don't like giving up, so we funded a group at Yale for several years before they even got to a point of having any publication at all. That's why we really set up this foundation in the first place, of course, so as to be independent of the tragedy of peer review of grant applications, and thereby to be able to do stuff that does not succumb to publish and perish. So yes, we were able to demonstrate how to make this stuff, first of all, rather than break it, but we were able to make it very cheaply in large amounts, and therefore you can do all the obvious things now, like raising antibodies to it and so on. And so now progress is very rapid, so rapid in fact that this group is now being spun out into a startup company that's going to be getting really rather good funding quite soon. The second one I'm mentioning here is actually our first spin out, the first time that we got a really big breakthrough to a sufficient level of proof of concept that it became investable, was now 6 years ago, and this company was started about 4 years ago. Actually, it kind of ended up running into the sand and having to be restarted, but that's now happened. So the idea that we might be able to break down oxidized cholesterol in our arteries and thereby cause atherosclerotic plaques to regress is one that I first put forward almost 20 years ago, and it's taken a while to catch on, but people think it's quite a good idea now. And enzymes have been found in bacteria that achieve this. Again, this is something that's missing from the hallmarks of aging paper. If you look at what they say about the accumulation of poorly digested waste products, it's restricted to proteins, which of course it should not be, because things like oxidized cholesterol matter just as much. I won't talk about the third one because you've already heard about it just before lunch from Sir Paul, whom we funded for, I think, probably 4 or 5 years, something like that, to work on exactly the stuff that he discussed. And I'm again very delighted to say that he, as he told you, has been able to create a startup company which is looking pretty promising in terms of its funding now, so that's all wonderful. I think I'm going to spend a little bit more time on the last point here. So back in 1986, if I'm not mistaken, some researchers at Andrea Meyer's newfound alma mater, in Melbourne, actually not the same university, it was at Monash, decided that they wanted to see what would happen if you would put genes that are normally found in the mitochondrial DNA into the nuclear DNA. And of course, if you just put them in without doing anything else, then they don't work. But the things that it seemed like you would need to do were pretty obvious, so they did those things, and they were successful with one gene in yeast. But it was sufficiently promising that everyone who worked on mitochondrial diseases and such like got very excited and applied for money to try to take the thing further, and they got the money, and they tried, and they failed, and they went back for more money, and they didn't get it, and they gave up. The usual story. So we didn't like that, and we decided to have a go at this, or this was, of course, sometime later. I, first came across this sometime after all that sorry episode had occurred. And so we started this as our first research project back in 2005. It took us 11 years to get our first publication in that area. Try that if you're subject to academic peer review. But it was now, we're now in a position where we've basically done it. This was our first paper 2 years ago, where we showed that we could express 2 such genes out of the 13 necessary ones at the same time in the same human cells. And they would work. They would completely rescue oxidative phosphorylation despite the existence of homoplasmic mutations in the mitochondrial DNA. And since then, we've used similar methods, a lot of trial and error, of course, but a lot of learning to get most of these genes more or less working. We've still got some way to go before we really have it cracked, but it's pretty much getting there. Yeah, that's a pretty good success story, and I must say, since mitochondrial mutations were my very first interest when I got into the biology of aging, I feel fairly happy that we were able to have the persistence that turned out to have been required. But what I'm going to do next, and what I'm going to do actually for the rest of my time, because I only have a total of 20 minutes, is I'm going to talk about the private sector. Because one completely incorrect thing that Sudhir said when he was standing up was that he was the only person here representing a company. You've already heard from Age Curve, which is Attila's company. Of course, he's doing it part-time at the moment, but we hope not for long. And indeed, I am now part-time working for a company as well as still being the chief scientist at SENS Research Foundation. You will see that there is a second logo at the bottom of all my slides, and that is the name of the company now headed by one of the absolute icons of this field of biomedical gerontology, namely Mike West, who started Geron back in the 1990s and then started Advanced Cell Technology, and now he's running a company which is focused on taking much of that same technology forward. AgeX has a number of interests, but it's mainly focused on stem cells and regenerative medicine in the classical sense of the term. One of our major themes is using stem cells that have been derived with unusually high purity. Of course, you all know that there are many different types of stem cell, and it's not much use putting the wrong kind of stem cell into the body for the thing you want to fix. So it's rather important to be able to create stem cells at high purity of the right lineage commitment, and we have technology that can do that much more effectively than anyone else can do. The other thing we're interested in is to induce a developmental regression, a kind of de-differentiation of cells actually in the body. This is something that other people have explored. Some of you may know work of, for example, the Belmonte group in San Diego, and also of Manuel Serrano's group in Spain, who have expressed the Yamanaka factors in mice in a manner that causes this to happen. We don't believe that this is the way to go. We think that it's never going to be possible to make that safe, rather than, there will always be a risk of inducing cancer. But we believe that using other genes, it may be possible to cause regression that cannot go as far as pluripotency, but can go as far enough to restore the regenerative capacity that we see in the rather less early embryo. The ability, for example, to regenerate after wounds without scarring. So that's the kind of thing that we're looking at. And it's pretty exciting. But I don't have slides from AgeX. I didn't nick Mike West's slides this time. So what I'm going to talk about instead is a few other companies. The one I'm showing you right here is another example of something that was actually missing from the Hallmarks paper. the type of molecular waste product that accumulates in the eye and causes macular degeneration is, again, not a protein. It is a derivative of vitamin A. And the same approach that we use, the exact same approach as we used for oxidized cholesterol in order to attack atherosclerosis, also worked. We found enzymes in bacteria that we could repurpose with a bit of tweaking to destroy this derivative of vitamin A. And this was sufficiently successful that we spun it out into a company a few years ago. It's now been very well funded. Its budget is considerably more than ours, even though it's not working on so many things. And I'm delighted to say that it's going to be probably in clinical trials within a year or so. So that's the kind of thing that happens when you get things spun out. You get people investing a lot more money than they're willing to donate. I'm very happy about that. This is Covalent, which is the original name of the company that Sudhir told you about, so I won't talk about that anymore. I do want to say a few words about this company, Aragos, which is run by the person who used to be our chief operating officer. Aragos, as many of you will know, is working on organ cryopreservation using a fantastic new technology, which isn't actually all that new, but has been repurposed again and improved. That involves cooling organs extremely rapidly by pumping helium through their vasculature, and it appears to very profoundly solve the problems of cryopreservation of solid organs that have historically existed. Of course, it's easy to see the application of this, the fact that so many people currently die of organ shortage, the fact that no one happens to be so generous as to die and to donate their organ to someone whose immune system is similar enough, or at least not when they are sufficiently nearby, so that the organ can actually be transferred to the recipient before it falls apart. If you could actually do this cryopreservation, then you are in a completely different world where we can get an organ across the entire world without it decaying, and indeed we can even bank them in large numbers so that we would be able to supply organs to anybody as soon as they need them. And that is the goal of this company. You all know about senescent cells, of course. Yet another thing that was missing in the Hallmarks paper was the idea of cells that are, in some sense, death-resistant. They hang out when we'd rather they didn't, but they're not classically senescent in the sense of elevated P16 or whatever. So an example would be the anergic T cells that accumulate in response to herpes viruses, for example. However, this company is mainly working on classically senescent cells, but rather than identifying small molecules that may be moderately selective in killing them, this company is looking at a genetic approach using suicide gene therapy to eliminate such cells. This would be the first time that suicide gene therapy would have been used clinically, and so, of course, it is a technological challenge, but again, it has sufficient promise and sufficient versatility that it has attracted the interest of quite a lot of investors. So this is just a few of the half-dozen companies that we have so far spun out. You know, 5 years ago, I couldn't really have imagined this. We were a pure play public charity, just, you know, relying entirely on donations. But now we can really say that our business model is to develop projects to a sufficient level of proof of concept that we can turn them into companies and they can receive investment. And that's what we will be doing going forward for as long as necessary. All right, how long, Vasa? How long? Yep, sure, no problem. All right, so in my last few minutes, what I'm going to do is just give you a proper feel for the fact that this is a drop in the ocean. This field, I believe, is not just an emerging industry. It will be rather soon the biggest industry of all time. I mean, like in the next 10 years or so. And that's despite the fact that it is currently focused on technologies that are still unproven. Think about it. You know, we've already got an anti-aging industry that's huge, despite the fact that it's based on products that have been proven not to work, right? So it's going to be interesting when we get ones that do work. But I want to first indicate how many companies there are now. Just 1 year ago, I believe I could have said, with my hand on my heart, that I knew of, well, I'd actually had contact with at least 3/4 of the most important and promising startup companies in this space. Now I'm down around 1/3 after 1 year. It's growing that fast. I'm just I've just completely lost the plot at this point. But I will give you a bit of a sense. I've told you about Ajax already. I'm listing a number of other companies here that have got funding from a number of very prominent sources, not just individual billionaire and angel investors, but also major established venture funds. I thought I'd just say a few words about Unity. Some of you may not know about Unity Biotechnology, which is the leading company right now working on the elimination of senescent cells. The thing I want to emphasize about Unity is this. They are worth nearly $1 billion right now. The actual amount of investment they have received is more than 300 million. And that was before they had even begun their first clinical trial, even phase 1. Now, if you think about the way that companies normally go and the way that investment normally comes in, that is just beyond imagination. That is possibly the single biggest message that tells you how big this industry is about to be. Now, of course, some investors are long-term thinkers, some investors are short-term thinkers, and they're going to get their money back pretty soon as well, because they're going to get it on the basis of these small companies either becoming enormous really, really quickly like that, or else being acquired by big pharma. But the key thing I want to emphasize is that this means a lot to you guys. Most people here I know, most of you are academics, and you may just not really like thinking about money very much, and I sympathize a lot with that. I don't understand money worth a damn. But the fact is, if it works, I like it, and this works. I've been saying since forever, certainly the people in the field have been saying since forever, that if we had a proper amount of money to actually do the research that we want to do, then we wouldn't be going so slowly. We'd be able to save one amazing number of lives. And that money is coming now, and it's not coming from the NIH. It's not coming through public funds. It's coming from the private sector. So I want everyone to understand that this is the time to embrace that. I think the UK in particular is being rather slow to embrace that. The US is certainly being fast, but mainland Europe is catching up fast, so that's pretty good. There are lots of ways to do it. This is a slide more for investors rather than for the investees, just to point out that you don't necessarily need to be a biologist to get into this in a manner that is clever. I'll stop there because I've run out of time, but I'd be happy to answer a few questions.
So it's very exciting, of course, but as an academic, you wonder, is the money going the right place?
Yeah, so is the money going in the right place? Well, the great news is that, yes, it is, because the investors are coming to me to ask me where to put it. Now, I mean, the reason that happened is because I'm simply not taking any money from anybody. If I started, being a paid consultant or whatever, then I would end up with all manner of conflict of interest issues. But luckily I have, just by virtue of the fact that I don't need the money necessarily, I'm able to maintain the authority that I've been able to acquire in the rest of the movement, and translate that into the private sector. So yeah, I mean, I'm actually, making a big difference now just by making sure that investments are sent in the right direction. And of course, I'm not the only one, but that's the main thing. And of course, every investor knows that every bet they make in any industry is a bet, and some things are not going to be the right bets. But so long as enough of them are right, that's good enough.
So compared to the peer review system, the funding mechanism used by investors, how do you rate the value of the two processes?
They differ by a factor of about infinity. I mean, the thing about the problem with academic peer, I'm not talking about academic peer review of manuscripts, that's different, okay, but peer review of grant applications. Having to convince your peers that what you're about to do is a good idea, and having to compete with all these other people to do, I mean, the main thing, of course, the main thing that I focus on is that it is intensely biased against high-risk, high-reward work. Intensely. You have to do the low-hanging fruit just in order to get the papers out, in order to be able to get your next grant application funded. That's the publish or perish paradigm. I didn't make that up. Everyone agrees with that. And this is high-risk, high-reward work. And it's on top of that, of course, it's all highly cross-disciplinary work, because this whole idea that I put forward so long ago is very much a divide and conquer strategy. And cross-disciplinary work also is vastly biased against by the peer review system. I just don't think it can be fixed. I think we need a system in which public money is allocated not by application to by telling people what you're going to do with the money, but rather by what you've already done that's demonstrated that you're actually quite good.
Hey, Aubrey, did you just close SENS? But are you saying we don't need SENS because
Yeah, good
there's
question.
so much more power in direct commercial
Yeah, thank you for pointing out that I accidentally took out my last slide. So we certainly can't say that yet. I mean, certainly our goal is to get to a point where we can indeed declare victory and say everything important is being done by other people. And I will be able to have a bit of a vacation, and that will be fine. But the moment we're definitely not there. There remain projects, including, for example, the mitochondrial project that I just talked about, which have not yet got quite far enough to convince investors that they can join the dots all the way to profit. And therefore, absolutely, the Foundation remains the essential engine room of the industry, if you like. We are still gestating projects, taking them up through to the point where they can actually be invested in, and those projects are every bit as important as the ones that are already one step ahead.
That's a tricky pitch, though, if you're telling people you're investing in something where 2 years down the line you could be making money from, but now it's just a donation.
So it turns out not to be so tricky. Yes, I agree, it sounds that way, but actually we have a way around that. What we say to investors is this. We say, look, here are some investment opportunities, companies that we have already created or that other people have created in parallel with us. These are good. But also, supposing you gave us money as well, then it's money down the drain. You won't get anything for it, except that if you give us even, as little as 100K per year, then you'll get as much of my time as you want. And that way, you will get access to all the information about the next startup, and you can be the founding investor of that one and make even more money. And it actually seems to work. I would say about half of the investors that we talk to actually do give us that kind of money just in order to get that access.
Break.